When working with numbers in science, especially in chemistry, a lot of the things that we deal with are very, very tiny, like atoms and molecules. And so to describe their sizes, we have to use extremely small numbers if we're using conventional units like millimeters or centimeters or, in the English system, inches. Conversely, if we want to talk about any sizable quantity that we can actually manipulate in the laboratory, we have to talk about very, very large numbers of those particles. And so it can be difficult to work with those very tiny or very large numbers in a conventional style format. And so this is where scientific notation comes into play. Scientific notation allows us to take a lot of those decimal places, which may not actually represent measured values or measured digits, and condense them so that the numbers that we do see are the important ones, the measured ones, the significant ones, and the rest of the magnitude, the rest of the decimal places that are just there because of the order of magnitude of the number, are represented by some power of 10. And so the proper format for scientific notation consists of two parts, what we call the base number, and that's the first part. And the second part is the power of 10. And again, that represents the order of magnitude that we are talking about in terms of the number. If we're going to convert from long form or decimal form of a number into scientific notation, the first thing that you need to do is to determine what the base number is going to be. And to get that, you take the original number and move the decimal point, whether it's expressed or in an understood position, and you move the decimal point so that there's only one non-zero digit to the left of that decimal point. In other words, the resulting base number should be greater than 1, greater than or equal to 1, and less than 10. The next part of the number would be times 10, and then in order to determine the power of 10, the number is going to be equivalent to the number of spaces that you moved the decimal point. The sign of that power depends upon the kind of number that you're starting with, whether it's greater or less than 1, and also which direction you're moving the decimal point. If you are starting with a larger number, a number greater than 1, then you've moved the decimal point to the left in the original number in order to get your base number. Consequently, you will have a positive exponent. If instead you had a number that started out less than 1 and you had to move your decimal point to the right, then you will have a negative exponent. So if we take this example 5,983, the decimal point is understood to be after the 3. To change this into scientific notation, you have to move it 3 places to the left, so the base number will be 5.983. And then the power of 10, we moved it 3 places to the left, so it's going to be a positive 3 power, and your final answer in correct notation would be 5.983 times 10 to the third power. If we take 0.00034 and convert this into scientific notation, first thing we notice is it's a number less than 1, so we know that the exponent is going to be a negative power of 10. When we move the decimal, our base number is going to be 3.4, and our power of 10, since we moved it 4 places to the right, is going to be a negative 4, hence giving us 3.4 times 10 to the minus 4th power. So if we take a look at some examples, the first one here, 5,900,000,000, if we convert that into scientific notation, the decimal point is understood to be at the very end after the last 0, and so to move that to make the correct base number, our base number is going to be 5.9, and we had to move that decimal 9 places to the left, therefore we would have a positive 9 power of 10, so your answer would be 5.9 times 10 to the 9th power. Please pause the presentation at this point and complete the remaining examples, and when you've finished, restart the presentation to check your work. In this next example, the decimal needs to be moved so that it sits between the 1 and the 2, which is a total of 9 places to the right. Therefore, your answer would be 1.2 times 10 to the negative 9th power. In the following example, the decimal point should come after the 4 and before the 9, so your base number would be 4.98, and your power of 10 is 5, giving you 4.98 times 10 to the 5th power. And in the last example, moving your decimal point 3 places to the right would give you an answer of 3.5 times 10 to the negative third power. If we're going the other direction, starting in scientific notation and changing to long form, again, we have to pay attention to the power of 10 and whether it's positive or negative. That will give us a clue as to what kind of number we're converting the base number into and which direction we should move the decimal. Remember that if you have a negative power of 10, that indicates you have a small number, a number smaller than 1. And so with a negative power of 10, you would move your decimal point to the left in your base number as many places as you have for the power of 10. If you have a positive power of 10, it means that your long form number is greater than 1, and therefore you'd move your decimal point to the right as many places as the power that you have. So taking a look at examples here, the first one, 3.61 times 10 to the 8th power. It's a positive power of 10, so we know that we're going to be moving our decimal to the right, and we need to move it 8 places. Now, as we move it, there are 2 places that are visible here, but after those 2 places, there's no more digits. In that case, you use zeros as placeholders. And so you would insert 6 zeros there, and your answer would come out to be 361 million. Please pause the presentation at this time and complete the remaining examples, and then restart the presentation to check your work. This first example here, 5.2 times 10 to the negative 5th power. The negative is telling you that the decimal needs to move to the left, 5 places total. After you move it the first place, you're out of digits, so you're going to need to insert 4 zeros as placeholders, giving you a final answer of 0.000052. The next example, 9.824 times 10 to the 3rd power. Positive 3 means you're moving the decimal 3 places to the right, which will give you a final answer of 9,824. And the final example, 1.4 times 10 to the negative 8th power. The negative 8 tells us we're going to move the decimal point 8 places to the left, and therefore our answer would be 0.000000014. When we do mathematical operations using scientific notation, sometimes it's easier to split the scientific notation into the 2 parts, the base number and the powers of 10. When you take the base numbers, if you split them apart, perform the operation, multiplication or division, as if there were no powers of 10 present. And then the answer that you get there, you save that until after you've worked with the powers of 10. What you do with the powers of 10 depends on whether you are multiplying or dividing. If you are multiplying with your exponents, you actually add the powers of 10 up. And if you are dividing, you subtract the powers of 10 in the denominator from those that are found in the numerator. And then once you've got those 2 separate answers, you can recombine them, and remembering that your base number should only have 1 non-zero digit to the left of the decimal point. It should be a number between 1 and 10. And so if your base number comes out less than 1 or greater than 10, you have to move the decimal point appropriately so that you do end up with a number in that proper range, and then also change the power of 10 accordingly based on how many places you had to move the decimal and which direction you had to move the decimal. Remember, if you shift the decimal to the left, you are making your power of 10 more positive. If you shift it to the right, you make the power of 10 more negative. If you are trying to input scientific notation into the calculator, different calculators are going to have different setups, but they all share basically the same setup and function. The first thing that you need to do is type in the base number, and then you need to access your calculator's exponent function key. Now, it might be a primary key, where it's the original use of the key, or it might be a secondary function, so you might have to hit shift or second, depending on the type of calculator you have. It might say EE, might say EXP, it might be a 10 raised to the X power button. Every calculator is different. On the TI-30X2S calculator, it is the second function of your inverse key, the X to the -1 power. And it displays as the blue EE seen here. So you would access that by pushing the second button in the upper left corner there, and then the X to the -1 key. When you press that function key, that tells the calculator that you're going to be inputting now a power of 10. And the thing to remember when you are putting in scientific notation in the calculator and using this exponent function key, do not manually type in times 10. That's what that exponent function key takes care of. If you manually type in times 10 as you're entering a scientific notation value, all of your values will be thrown off by an order of 10. Taking a look at these examples, in the first one you're multiplying 9.28 times 10 to the 4th power times 6.1 times 10 to the negative 7th power. Remembering the steps, split the parts and multiply your base numbers first. Using estimation, roughly 9 times 6, we would expect our answer there to be 54. Putting it in proper scientific notation form, we would expect our answer to be relatively close to about 5.4. So we'll remember that for the end. With the powers of 10, in multiplication, you add them together. So we should be somewhere around the 10 to the negative 3rd power. When we put it all together, making that adjustment of the decimal point one place to the left, we should get an answer of 5.7 times 10 to the negative 2, or 0.057 in long form. And that 5.7 base number is close to what we estimated, so we can be reasonably sure that our answer is correct. Take a moment now and pause the presentation, try the second example problem, and when you're finished, resume the presentation to check your answer. Taking a look at this problem, here you have two separate operations going on, first multiplication in the numerator and then division. So take the same set of steps that we've talked about, do the base numbers first, get that number, and then your powers of 10, add the two exponents in the numerator to give you 7, and then remember in division you take the numerator minus the denominator exponents. So 7 minus 10, you come up with a negative 3, and combine that with what you got for the base numbers, and you should come up with an answer of 1.18 times 10 to the negative 3rd, or in long form 0.00118.